We know that there are millions of organic compounds. So if we had to memorize how each and every one of them reacts, studying organic chemistry would be a very tough job, right? Fortunately, organic compounds can be divided into families and all the members of one family react in a very particular manner. What determines the family of an organic compound is really the functional group. The functional group is a structural unit that acts as a center of reactivity of that molecule. We have looked at some of the common functional group in last classes and we are already familiar with various functional groups. So, in this lecture we are going to study the reactions of alkenes, but before I go over reaction of alkenes, I want to point out that alkene, which is the carbon-carbon double bond, all the alkenes pretty much react in a similar way. Whether the compound is a really small molecule like ethene or a really large molecule like cholesterol, both these molecules are going to react the same way in a particular reaction. So, herein I have an example of an alkene reacting with HCl and it reacts such that the carbon-carbon double bond breaks, right. So, this bond is broken in the end product and HCl adds on the carbon-carbon double bond, right. So, hydrogen adds to one carbon and chlorine adds to the other. The same thing will happen if I take cholesterol molecule. So, now if I look at cholesterol here, I have this carbon-carbon double bond and when HCl reacts, it is going to do the same reaction. So, it is going to form this. Right. So, irrespective of the kind of molecule I have, I can determine its reactivity based on the functional group it has. So, this is really key to understand the reactions of organic compounds. One of the key things which we wish to practice before we really start learning organic reactions is not to memorize them, because remember that even if you want to memorize one of the functional groups and one of its reactions, remember that there are multiple reactions of each functional groups. So, if you really memorize a reaction, organic chemistry becomes really dull and dry and really becomes a memory based subject. Whereas, if we really look at organic chemistry reactions and understand why a particular reaction is taking place, then this whole activity of memorizing these vast reactions really is not needed, and you can really understand a reaction by just looking at the functional group, by just looking at the compounds that are reacting, and will be able to predict the product. So, what we are going to do is we are going to rather recognize the structure of the functional group and understand their behavior. So, you can really imagine each functional group to have a characteristic nature. Just like some of our human beings some are fun loving, some are really serious. The same way functional groups are also very characteristics. Some of them are acidic, some of them behave in a particular manner, some of them have nucleophilic center, some of them have electrophilic center, and thus instead of remembering each reaction, if we understand the chemical logic, the structure of the functional group, then it becomes much easier for us to master the reactions in organic chemistry. To further reduce the need of memorization, we need to understand why a functional group reacts the way it does. It is not sufficient to know that a compound with a carbon-carbon double bond reacts with HBr to form the product, wherein hydrogen goes to one carbon and bromine goes to the other carbon. We really need to focus on why is this compound reacting with HBr, right. So, henceforth, whenever we are studying reactions of any functional group, we are going to focus mainly on why is this really happening. So, anytime you are confronted with any new functional group or any new reaction of a known functional group, you should focus on how the nature of the functional group allows it to do that reaction. Then, when you are confronted with a reaction you have never seen before, or a molecule that you have never seen before, you can still apply the knowledge of how the structure really determines the reactivity of the compound, and it will really help you to predict the products of the reactions of the compounds that you have never seen before. Organic chemistry is all about interactions between electron rich atoms and electron deficient atoms or molecules. It is these forces of attraction that make chemical reactions happen. From this follows a very important rule that determines the reactivity of organic compound. Electron rich atoms or molecules are attracted towards electron deficient atoms or molecules, right. So, electron rich atoms really want to attack electron poor atoms or molecules, that is what we are going to remember. Each time we study a new functional group, remember that the reactions that it undergoes can be explained by this very simple rule. Therefore, to understand how a functional group reacts, we must learn to recognize electron deficient groups and electron rich groups. Okay? So, we are going to look at two new terms here. So, the first term that we are going to look at is called as an electrophile. If you look at this particular word, the part phile means loving, right. So, this is electron loving, right. So, electrophiles are electron deficient atoms. So, that is why they love electrons, they want to get electrons, right. So, they do not have their own electrons. So, an electrophile can have an atom that accepts a pair of electrons, or it can have an atom with an unpaired electron. And therefore, it is in need of the electron to complete the octet. So, what are the different electrophiles you have seen before? Really in any acid base reaction, the acid is an electrophile because the base with its lone pair of electrons is attacking the proton to grab the proton from that acid, and that proton is really the electrophile here. Other electrophiles that you must have seen are like BH3. So, we talked about the structure of BH3 in our first class, and we said that boron has an incomplete octet. So, it becomes an electrophile. Let us take a bromine with one less electron, and that becomes an electrophile. Or you can also have a carbocation, right. That carbocation is deficient of a pair of electrons, and thus it is also an electrophile. In contrast, we have a different terminology for the compounds that really love a positive charge. So, these are nucleophiles. So, remember, phile again means loving, and nucleophile means the compound that really loves a nucleus that is positively charged. So, a typical nucleophile has a pair of electrons it can share. Some nucleophiles are neutral, whereas some of them are negatively charged. And because the nucleophile has electrons to share, a nucleophile is typically the compound that will first go and attack a particular electrophile and will try to share its electrons with that electrophile. Okay. And typically, as you can see, one of them is electron loving, one of them is nucleus loving. So, electrophiles and nucleophiles really are the key players that react with each other since they are attracted to each other. Okay. So, most of the organic chemistry reactions can be summarized by just one statement that a nucleophile is reacting with an electrophile in this reaction. So, now let us look at some of the examples of nucleophile. So, in water, the oxygen atom has a pair of electrons it can attack with. So, oxygen here becomes a nucleophile, or you can think of ammonia, you can think of hydroxide ion, you can also think of chloride, bromide, you can also think of various other nucleophiles. So, negatively charged ions or molecules that have a potential of attacking in a chemical reaction will be termed as a nucleophile. So, now let me ask you a question, which part of the carbon-carbon bond or which part of the alkene moiety is really nucleophilic, which part of it is really electrophilic, right? That is the question we want to ask, because we want to start looking at an alkene's reaction like it is a reaction between a nucleophile and electrophile. So, I have the structure of an alkene here, and if you really see, these are the two carbon atoms. As we said, there is a sigma bond here in between these two. This is the pi bond that exists above and below the plane, and rest everything is in the plane of the paper, right. So, where are the electrons in this molecule? Which part is really going to get attracted to an electrophile? As far as I can see, in an alkene there is no positive charge. So, I do not see an electrophile directly, but if I can really see that the pi cloud here, right. So, this is the sigma bond and these are the pi bonds, right, above and below the plane. The pi bonds are really loosely tied to the carbon atom, right. Because sigma bond is stronger, pi bond is weaker, the pi bond is easier to break, right. Also, the pi bond is really rich in electrons. So, if I want to see the reactivity of an alkene molecule, I will call it to be a nucleophile. It is a really electron rich molecule. So, the cloud of a pi bond or the cloud of the pi electrons can attack an electrophile in a chemical reaction. Okay. So, we can therefore predict that an alkene will react with an electrophile and in the process the pi bond will break. So, for example, if a reagent like hydrogen chloride were to be added to alkene, the alkene will react with the partially positively charged hydrogen of the hydrogen chloride and a carbocation will be formed. So, what we are going to do is we are now going to look at this particular reaction that we first saw. We are going to look at the reaction between an alkene and HCl and we are going to see how the electrophile and the nucleophile really react in the reaction. So, if I take 2-butene and I react it with HBr, if you really think, we said that our nucleophile is the alkene and the electrophile is HBr, right. So, what will happen in the first step is that the double bond of the alkene, it is going to be really electron rich, it is going to go and attack that proton on HBr because that hydrogen bromine bond we know is partially polarized bond such that most of the electrons are with bromine and the hydrogen already has a delta positive. So, if I want to denote the charges, there will be a delta positive on hydrogen and a delta negative on bromine, right, a partial positive on hydrogen. So, the electrons are going to get attracted to the positive charge. So, the way I show it is that I draw an arrow from the middle of the bond towards that hydrogen. Okay. So, the arrowhead has to go from the middle of the bond to the hydrogen, not the other way around. I cannot draw an arrow from the hydrogen to the double bond, that is wrong. Okay. So, when we are looking at the reactions, we are also going to focus on how the arrow pushing happens. Okay. So, we have to draw an arrow from the 2 electrons of the pi bond of the alkene towards the positively charged proton. Okay. Now, the proton does not want to really form 2 bonds, it is already forming a bond with the bromine, it does not want to form a new bond with the carbon. So, what it does indeed is it breaks its bond and gives the electrons to the bromine. So, what do we have here? As a result of which, now the carbon has formed a bond with the hydrogen, right. So, I am going to give the hydrogen to the first carbon and form a bromide ion. If you think about it, if I number my carbons 1 and 2, as the reaction happened, as the carbon attacked the proton, carbon number 1 got the proton, right, carbon number 1 got the hydrogen to form bonds with, whereas carbon number 2 really lost a bond in the reaction, right. So, it had the double bond electrons, now it no longer has the double bonded electrons. So, thus as this reaction happens, what we give rise to is a carbocation and a bromide ion, right. So, this is our carbocation. Now, in the next step, what is going to happen? Think about it. The bromide ion is right there, right, and you have formed something positively charged. So, what will happen? The positively charged carbocation is going to be attracted towards the negatively charged bromine and in fact bromine with its electrons is going to attack on that positively charged carbocation. So, what we are going to do is we are going to see the next arrow pushing such that, let me just redraw my carbocation here. So, the bromide with its electrons is going to attack on this carbocation to give you addition of bromine on one of the carbons, right. If I really think about it, one of the hydrogens got added in the first step and the bromine got added in the second step of the reaction. So, what I have done here is that throughout the reaction what we are doing is we are adding a hydrogen and a bromine across the double bond, right. So, this is an addition reaction wherein 1 mole of HBr when it reacts with 1 mole of alkene will add across the carbon-carbon double bond and form 1 mole of the final product, that is the alkyl bromide. Since we have added an electrophile to the carbon-carbon double bond, in our case the addition of electrophilic H plus happens towards the alkene in the first step, right. So, our first step which was the addition of an electrophile, so this whole reaction is termed as an electrophilic addition reaction. Okay. So, we are going to call this as electrophilic addition reactions. And remember that we have added HBr right now, but HCl reacts the same way, HI reacts the same way, H3O plus will react the same way. So, really addition of any acid will really be termed as an electrophilic addition reaction with the alkene. So, now we will look at the animation of this reaction. Electrophilic addition reactions are one of the characteristic reactions of the alkenes. So, what I am going to go over is now we are going to write down 2 more reactions of various alkenes reacting with HCl, HI, H3O plus, right. So, let us take the example of cyclohexene reacting with H3O plus. Again, the first thing I think about is that where are the electrons and where is the electrophile, right. So, electrons are present on the carbon-carbon double bond. So, that is my nucleophile, and a positive charge or an H plus really exists in H3O plus. So, that is the electrophile, right. So, what we are going to do is we are going to take the carbon-carbon double bond, it is going to really take its electrons and attack that proton, and the proton does not want to form 2 bonds at the same time. So, what it is going to do is it is going to put those electrons back on that oxygen, right. As a result of which what happens is you give rise to a carbocation, okay. Remember there were 2 protons to begin with here. So, you give rise to a carbocation and water molecule, right. Okay. Now, what happens? Now, you have a carbocation that is formed, positively charged carbon, and you have a water molecule where the oxygen has the pair of electrons, right. So, what we are going to do next is that oxygen is going to attack here, as a result of which what happens is we are going to form this particular species. Now, you may wonder, is this the end of the reaction, right, because we have done the 2 steps. In the first step the nucleophile attacked the electrophile, in the other case the ion or some moiety that had electrons has now come and attacked on the carbocation. But remember our 5-star principle, the very first class, we said that nature hates charges. right. So, what we have right now is a charged molecule, it has a positive charge. So, it is not going to remain like that. In fact, when we are working with water or when we are working with hydronium ion compounds like this, we have a lot of other water molecules in the reaction, and one of the water molecules really is going to come and grab that proton and put the electrons back on that oxygen. So, what do we form? We form addition of an OH and H across the carbon-carbon double bond. So, if you really see, we have done nothing but addition of hydronium ion across the carbon-carbon double bond, right. Okay. So, let us take one more example. I am going to take the reaction of an alkene, ethene, and react it with HI. Okay. Now, one thing I want to do here is I want to write down the product directly without going through the mechanism. Remember, the mechanism is vitally important and it will allow me to write down the product of any reaction. As long as I know the mechanism, I can predict the reaction product. So, in this case, I know the mechanism. What happens when an alkene reacts with an electrophile like this? The double bond breaks and one of the carbon will form bond with a hydrogen, the other carbon will form a carbocation, and the I minus is going to go and attack that other carbon. So, what are we going to form here? Addition of iodide on one of the carbons and addition of hydrogen on one of the carbons, right. In all, we end up adding this HI on the carbon-carbon double bond, right. Okay. So, we have covered the first reaction, which is the addition of HCl, HI, HBr, H3O plus on the carbon-carbon double bond. But remember, because the alkenes in the earlier reactions have the same substituents on both of the sp2 hybridized carbons, it is really easy to determine the product of the reaction, right. It did not matter where I put the iodide, it did not matter where I put the hydrogen, which carbon gets the hydrogen, it really did not matter. So, it was very easy to determine the product. Okay. But what happens when the alkene does not have the same substituents on both the sp2 hybridized carbons? Which sp2 hybridized carbon will really get the hydrogen, right. So, that is one question. So, what I am going to do is, I am going to really react 2-methyl propene and we are going to add HCl to it, right. So, let us take 2-methyl propene. So, this is propene and this is 2-methyl propene, right. So, if I really see, this is my starting molecule. Now, the question is, if this molecule reacts with HCl, what is going to happen? Okay. Remember that how I said that each alkene will react in a very particular manner? The answer is yes, it will still do the same reaction. But now, the question is, which of these carbons, 1 or 2 will get the hydrogen, or which of the carbons will get the chlorine. So, if I really give the hydrogen to the first carbon, I form this product, or if I give the hydrogen to the other carbon, I form this product, right. Remember, these are two different molecules, one of them is tertiary butyl chloride and one of them is isobutyl chloride. So, now the question arises that if this molecule reacts, which one will it form? Okay. So, we are going to now look at reactions wherein the alkene is asymmetric to begin with. Now, let us think about the first step of the reaction. The first step of the reaction is when the double bonded carbon goes and attacks the proton, right. Now, remember, the question is which of these carbons will prefer to have a hydrogen attached to it. In order to really understand the logic behind what is happening, we need to understand the product that it forms. So, let us first try to attack this double bonded carbon on the hydrogen and kick off the chlorine, right. If carbon number 1 gets the hydrogen, this is how the molecule will look like, right, the end product of the first reaction. whereas if carbon number 2 gets the hydrogen, this is what the product looks like, right. So, what we have here really are two different molecules, two different carbocations. Which carbocation will form will be determined by the energy of these carbocations. Remember, nature hates charges, right. So, if I have a charge that is really unstable, nature is not going to favor the formation of that charge, right. So, between these two charges, which one is really stable, right? The answer to this question is that we have to look at what really governs the carbocation stability. And before we even go and look at the stability of carbocations, let us first look at the structure of carbocations, right. So, herein I have a model of a methyl carbocation. Okay. A carbocation is sp2 hybridized. So, methyl carbocation, which is CH3 plus, has 3 bonds with the 3 hydrogens and they are all in the same plane. So, this is a flat and a planar carbon hydrogen bond molecule, right, trigonal planar geometry. What really happens is that above and below the plane, the carbocation has a empty p orbital, right. So, this is where the vacancy is, right. So, remember the second step where the bromide ion came and attacked the carbocation. This is the position where the bromide ion is going to come and put its electrons, right. So, a carbocation is really sp2 hybridized, trigonal planar and has an vacant p orbital here, right. So, now for such a molecule, what will really govern its stability? If you think about it, anything that can put electrons into this empty p orbital, that can make the carbon more electron rich, because right now it does not have a complete octet, right. So, if it can gain electrons in any way, that particular species is going to be really stable, right. So, now between these two carbocation compounds, we want to figure out which one is really more stable based on which carbocation, which positive charge can gain electrons from the surroundings. So, carbocations are classified according to the number of alkyl substituents that are bonded to the positively charged carbon. A primary carbocation, so for example, this one here has one substituent, one alkyl group attached. A secondary carbocation will have 2 alkyl groups attached and a tertiary carbocation will have 3 alkyl groups attached. In fact, I have also drawn a methyl carbocation which has no alkyl groups attached, only hydrogens attached to it. The stability of a carbocation increases as the number of alkyl groups that are attached to the positively charged carbon increase. So, tertiary carbocation is going to be most stable and methyl carbocation is going to be least stable, and the stability is going to increase as we go towards tertiary carbocation. Here we are talking about the relative stabilities. Carbocations are really not stable species. So, even in the tertiary carbocation, when we say it is stable, it is not really stable to isolate from a reaction medium, right. There are very few carbocations which are stable enough such that they can be isolated and stored in the bottle. But remember, when I say that tertiary carbocation is really stable, what I mean is amongst all the carbocations, a tertiary carbocation will be more stable. So, we are all talking about relative stabilities here. So, why does the stability of a carbocation increase as the number of alkyl substituents bonded to it really increase? Alkyl groups decrease the concentration of positive charge on the carbon. Remember what we said, that the middle carbon here is electron deficient, it has a positive charge, it has an empty p orbital, right. So, anything that can put electrons into the system such that they decrease this charge, because nature hates charges, right. So, anything that decreases the charge on that carbon, we are going to have a favorable stabilizing interaction, right. So, how do alkyl groups decrease the concentration of positive charge on the carbon? For this, we need to recall that the positive charge on a carbon signifies the empty p orbital, and for example, in this one, the adjacent CH bond, right. So, let us take the example of a methyl carbocation versus an ethyl carbocation. So, what I am going to do is, since carbocations are trigonal planar, we are going to show the geometry correctly. We are going to show that they are trigonal planar, whereas if I take an ethyl carbocation, that is how it looks, right. If you think about it, the adjacent carbon hydrogen bonds for the ethyl carbocation, okay. So, this orbital here, whereas you have the MTP orbital here on this carbon, that is carbocation. What happens is the bond electrons of this CH bond get polarized towards this positively charged carbon, okay. No such overlap is possible here. In methyl carbocation you cannot have that overlap, but in this case what happens is that the CH bond electrons of the adjacent carbon can overlap slightly with the MTP orbital. Remember, I am not moving the electrons, we are not taking the electrons from the CH bond and putting it on that carbon. It is just a polarization, it is slight movement towards that positive charge, right. So, this movement of electrons from the sigma orbital towards the vacant p orbital of the ethyl cation really decreases the charge on the sp2 hybridized carbon, and really this causes a partial positive charge to develop on the carbon really bonded by the sigma bond, right. So, when this particular process happens, what happens is the charge on this carbon goes down, whereas there happens to be a slight charge, a very slight charge develops on this other carbon, okay. As a result of this, what has happened? A positive charge is no longer localized on that carbocation, a positive charge is now spread out over a greater volume of space. And when we were studying acids and bases, this is what we talked about, right. Dispersion of charge really helps the molecule to be stable, right. So, in this case, the dispersion of the positive charge really stabilizes the carbocation, because charge species is more stable if the charge is spread out. Nature hates charges, that is what we always remember, right. So, delocalization of electrons by the overlap of this orbitals is really called as a hyperconjugation. So, we are going to learn a new term here, this is called as hyperconjugation. Okay. Hyperconjugation does not mean that we move the electrons all the way, it is just a slight polarization. Now, really if you see, this particular carbon here has 3 carbon hydrogen bonds. So, the question is which one will really overlap? The truth is it has to align in the geometry. If it aligns very nicely in the geometry, that particular sigma orbital will overlap its electrons on the positively charged carbon, okay. And hyperconjugation really only occurs if the sigma orbital and the empty p orbital have the proper orientation, okay. But really the proper orientation is always easily achieved, because there is a free rotation between the carbon-carbon s bond, right, that is what we saw in the first class. If I really see this tertiary butyl carbocation here, there are 9 carbon hydrogen bonds that can potentially overlap with the MTP orbital, such that the positive charge of the carbocation gets spread out on the whole molecule, right. So, the reason why as we go on to the tertiary carbocation it becomes more stable is that just that there are more CH bonds, there are more of these sigma orbitals electrons that can potentially overlap with the MTP orbital. So, now let us go back to our question and now answer this question, which one amongst these two is more stable, this one or this one? If you really see the carbocations, in this case the carbocation is attached to, this is a tertiary carbocation, whereas in this case this is a primary carbocation. So, which one is more stable? Of course, the tertiary one. So, what happens is this carbocation will be formed in excess, okay, because it is more stable, the formation of that carbocation is much more favored, and thus what will be the product that will be formed? So, the product that will be formed will arise from this particular carbocation, and the product of our reaction here that arises from this carbocation is the first one. So, this will be the major product of the reaction, and the other product will be the minor product of the reaction. We are going to see couple of more examples wherein we start reacting with the asymmetric alkenes. So, now let us look at some more reactions. Okay. So, I am going to take this example, right, and we are going to react it with HBr. So, this is methyl cyclohexene and we are reacting with HBr. Again, if I see the two possible carbocations that could be formed, first on carbon number 1, such that the hydrogen goes to carbon number 2 in the first step. Again, focus on the arrow pushing, the double bond attacks the proton, the bond between hydrogen and bromine breaks. Arrows have to be pushed from the electrons towards the positive charge, right. So, you can either form this or you could form the other carbocation and give the hydrogen to the first carbon, right, and of course, you are forming a bromide ion. Now, the question is which one amongst these two really forms, right. If I see this clearly, this is a secondary carbocation and this one is a tertiary carbocation. So, the tertiary carbocation will be formed in excess, will be formed faster. So, what we are going to do is, we are going to attack the bromide on to this tertiary carbocation, giving rise to our major product, which looks like this, right. Whereas, the other product which arises from the other carbocation is really the minor product, right. So, let me draw the minor product as well. So, the minor product is going to arise from this carbocation. So, when the bromine will attack here on this carbocation, I will give rise to the minor product, right, but the reaction is predominantly going to give me this particular alkyl halide. Okay. So, the major product obtained from reaction of addition of HBr to 1-methyl cyclohexene is 1-bromo 1-methyl cyclohexane. So, in both cases the more stable tertiary carbocation is formed, that is what we saw. It is formed much more rapidly than the less stable secondary carbocation. So, the major product of each reaction is the one that we are forming from the tertiary carbocation. If you really see these two products, the major and the minor product here, these are constitutional isomers of each other. So, we have looked at different isomers. What is the relationship? They are constitutional isomers. Why are they constitutional isomers? Because they have the same molecular formula, but different structural formula, their connectivity is different, right. So, the constitutional isomers, they differ in the way their atoms are connected. A reaction such as this one, in which two or more constitutional isomers could be obtained as products, but one of them is predominant. So, in this case the major product is predominant, is called as a regioselective reaction. The reaction is selective in the region that it operates. There are degrees of regioselectivity. A reaction can be moderately regioselective, highly regioselective or completely regioselective. So, a completely regioselective reaction does not form the minor product at all, it only forms one type of product. In this case, addition of alkene with HI, HBr, hydronium ion or electrophilic addition on the alkene, it is highly regioselective, meaning the major product really predominates 80%, 20%, right, that will be the ratio between the major and the minor products. Moderately regioselective reactions are like 60-40, whereas there are reactions that are not regioselective at all. So, they will form both the products in equal distribution, but this one is highly regioselective. Okay. We have now seen that if we want to predict the major product of an electrophilic addition reaction, we must first determine the relative stabilities of the two positive carbocation intermediates. Around 1865, when the carbocations or existence of carbocations, the relative stabilities were still not proven, Vladimir Markovnikov published a paper in which he described a way to predict the major product obtained from the addition of hydrogen halide to an asymmetric alkene. So, he used a shortcut which is also called as Markovnikov's rule. In his rule, what he states is that when a hydrogen halide adds to an asymmetric alkene, the addition occurs in such a manner that the hydrogen attaches itself to the double bonded carbon atom of the alkene bearing the lesser number of hydrogen atoms. Okay? Because H plus is the first species that adds to the alkene. So, if I have to really think about Markovnikov's rule, Markovnikov rules is nothing but it is talking about the stability of the carbocation. If I have to now state the Markovnikov's rule again, knowing that the carbocations exist and knowing that their relative stabilities are such that I would always say that the hydrogen adds to the carbon-carbon double bond such that a more stable carbocation is formed, right, that is more substituted carbocation is formed. That is how I would remember the Markovnikov's rule, because not always you will have hydrogens attached to the carbon-carbon double bond. Sometimes you may have a carbon-carbon double bond that does not have any hydrogens. So, the right way to remember this rule would be such that the double bond attacks on the hydrogen halide such that the hydrogen goes to the carbon such that the carbocation that is hence formed is much more stable, right. Okay. So, we will continue with the reaction of alkenes in the next class.